Hello, and thanks so much for joining us here at FutureCon Central. Today we have quite an interesting topic for you all, and we're going to discuss securing AI models in the cloud. My name is Gabriel LeBeau. I'm the Manager of Business Development here at SafelyShare, and I'm also joined by our CEO and co-founder, Shamim Naqvi. Just in general, training AI and ML models has far-reaching security implications that relate to data privacy, adversarial attacks, bias amplification, as well as things like model inversion attacks. The protection of this sensitive data, as well as guarding against these sorts of manipulative attacks, any sorts of biases, require implementing very robust security measures that are essential in mitigating some of these risks. So I'll pass it off to Shamim to introduce himself quickly.
Hi, Gabriel, and thank you for having me. We at SafelyShare are very much interested in this topic, and the company is geared towards that. So thank you for asking us to come over.
So we've prepared some slides to walk through today. The format of this presentation is going to be just an open dialogue between myself and Shamim, and we'll go through some of the industry trends, some of the challenges, and some of the ways we can address these challenges as well. So firstly, in regards to some of the overall industry trends and why this is a hot topic in the first place, the first idea here is that we're at somewhat of an inflection point in terms of how companies are evaluating how they're going to use AI. And there's a couple of requirements to consider here in order to actually leverage a technology like this. It has to be fed with really good data, and it has to be something that as it becomes mainstream, we're isolating those particular use cases. So Shamim, what do you think some of the most important trends as well as challenges that come about when discussing this are?
Well, it's extremely well known that the more data you have, the better data you have, the better the model, the better the training of the AI system, and better the results. So it's all about the data. AI and model building, model training, model serving is all about the data that you get. And sometimes people will tell you that the highest value data is data that has a lot of private stuff in it because it is the hardest to find, but it is the most accurate. So therefore, the challenge is you have large amounts of data, and it almost certainly has lots and lots of private components. How do you protect the data? How do you protect the model? How do you train the model? But how do you maintain the security and the integrity of the model at the same time? So it's all about the data. It's a huge data-intensive operation.
Absolutely. And what do you think some of the more common use cases are? Is this something that is more prevalent in certain fields like medical or fintech or payment processing? What are your thoughts there?
Well, there's hardly a segment of the market that is not touched today by some aspect of AI. There's the traditional areas were medical, healthcare, etc., and financial applications. One of the first few use cases were sort of involving financial services where consumers' debt applications were being processed using AI technology. It was called expert systems in those days. Mm-hmm. One of the earliest expert systems was a blood diagnosis, disease diagnosis system called eMyCin out of Stanford University. But nowadays, it's sort of extremely hard to tell which is more suitable. The models are being used in healthcare, models are being used in genomics, models are being used in molecular genetics, models are being used in the financial sector, models are being used in bioethics applications, etc. So it's the usage is sort of exploding into many, many, many verticals.
Right. So it's safe to say that in order to keep up with this new industrial revolution, companies are going to be using AI in some capacity at some point.
And in fact, it could be argued that if you're not using AI and machine learning at some point, then perhaps you should think about why you're not using it.
So there are a few more trends here that we can evaluate from Gartner here. There's a few different ideas of what some of the challenges and implications of these industries starting to use AI technologies will look like. Firstly is the idea of transparency and being able to see into these models and understand what the goals of the model are going to be, what it's supposed to produce, as well as what it's going to be trained on. There's also quite a bit of conversation.
It's sort of interesting that you started with that.
Yeah.
How do you know if you run a model and the model makes a prediction? How do you know the prediction was made by the model?
Exactly.
How do you know that this particular bit of inference, this particular bit of insight is coming from a model? Because you may not be present when that inference was made. So is there a certificate that comes with this prediction that says, oh, this is from ChatGPT or this is from model 1, 2, 3, 4? How do you verify that the prediction that you are being presented is actually coming from a model? And how do you verify that the model, in fact, is untainted?
Mm-hmm. And this could represent, I think, one of the risks represented by AI and ML training that people don't traditionally think of. I think when people start to think about the use of private data for training these models, the first thought people have is leakage and that data escaping. But the point you bring up is more along the lines of intrusion. So people actually being able to maliciously manipulate the model to produce an output that may not be valid. So that's definitely a very interesting point as well.
Yeah, you see, the hallmark of an AI system is that it is not simply retrieving a piece of data that has been previously stored and presenting that piece of data to you.
Mm-hmm.
It is actually doing an inference. What it's trying to tell you or what it tells you does not have an explicit form in a database someplace.
Mm-hmm.
It is derived from the data. It is a piece of heuristic evidence derived using certain machine learning principles. So you cannot say, show me the record that has this. If in normal circumstances, if you asked for the salary of a person or the price of a particular item, you would be able to point to the piece of data from which that answer came. But in the case of an AI inference, you are being told that the price of an item is, or the price of a house, for instance, is not known, but is conjectured to be $1.2 million.
Right.
Why should you believe that?
Yeah, there's an aspect of trusting the model, and that trust has to be based on security as well. But I think the final point here is pretty interesting as well. Gartner predicts that at least one company will see some AI deployment banned because of non-compliance. So one of the other aspects here is making sure we're conforming to whatever those compliance standards end up being. So what do you think some possible pitfalls are there?
Congress is very busy contemplating coming up with the legislation.
Mm-hmm.
Congress seems to feel that they missed the boat on legislating social media.
Mm-hmm.
And based on some remarks which I read, they don't want to repeat the mistake and miss the boat on legislating against AI systems. So no one knows what form that legislation is going to take. Mm-hmm. One hopes that it won't stifle research and development in machine learning technology and AI technology.
Yeah, I think it's always beneficial to have these sorts of conversations and have them with people like yourself, as well as I think you're referring to Sam Altman testifying in front of Congress, and he's somebody that obviously would never want to stifle development, but at the same time wants to do it in a safe way, and I think that's the same case with you. So.
Yeah, you see, let me raise a somewhat of a technical point here. Mm-hmm. Deep learning models that are producing these fantastical results have a fundamental issue today, when the issue is that there is no causal explanation of the results. There is no way to verify the results to say that this is an explanation of the result. So you have to, the best that you can say is that from all the testing that we've done, this model is correct 60% of the time or 72% of the time. But in this one particular case that it's making a prediction about you or somebody close to you, what is the basis of that prediction? The system is unable to proffer an explanation, a causal explanation. When you go to a physician and the physician gives you some news about something that is wrong with the patient, the physician usually gives you a causal explanation. There is no causal explanation here. So that is one of the disconcerting things, but it's also the most powerful thing that distinguishes machine learning and machine learning systems from the usual kind of computational tasks.
Right, and maybe this will end up being a development within some of these large language models or any sort of ML-based models that could be able to provide at least some sort of explanation from a mathematical standpoint, or maybe businesses and humans in general will learn to just have an implicit trust in these sorts of models, and that could be a positive or a negative, but we'll see what happens there.
Well, my fear, and perhaps the fear of many people in this field, is that as the models make more and more sophisticated inferences, it's quite possible that the mistakes that they make will also be quite subtle. So for example, in some cases, ChatGPT generates extremely plausible sounding answers, but it has been noticed that sometimes it makes quite subtle errors. Sometimes, of course, it makes non-subtle errors as well. And those are easy to find. But the subtle errors, those are the risky ones. I mean, that's where it becomes a little scary, that it takes an expert. If it takes an expert to find out that there is a mistake in what ChatGPT says. Yes, we know and we've read all the disclaimers, etc. But if it takes a sophisticated expert to reason about some of the statements being made by a machine learning model, we really need to be very careful and understand the basis of some of these responses coming out from machine learning systems.
And that's kind of related to one of the second points that Gartner makes here. And maybe instead of having a human expert verify some of these answers and take a look and try to determine where these errors are coming from, or if they're even present, is the idea of having an AI do it. Why wouldn't you be able to have a separate model trained on the outputs of another model to determine if they're valid or not?
Because there is something in computing theory that's called the halting problem. You can't have programs who verify the output of programs. There can be no solution to the halting problem. It's known to be one of the undecidable problems in computer science. So you can't do that. You can't have an AI program explain the conclusions of a different AI program. It might work for one case, but it will not be able to do it for all cases.
Understood. Interesting.
So I've previously said that machine learning is a data-intensive game. Here is a simple way to understand what the process of the training and the development of a machine learning model happens to be. You start with some huge amount of data that you have collected somehow. Perhaps it's in a data lake. And you create extracts that you plan to use, those data extracts that you plan to use for what is called model training. In the model training phase, you have a certain machine learning algorithm, and you feed these data extracts to this algorithm, and the algorithm creates a model or builds a model. And let's say that you now want to know, after several hours of running, or perhaps a day or two of spending the time that you have spent to build this first model, you want to know if it's any good. So you run the model on some test data, and you find that its performance level is not acceptable. So you go back and you retune the model parameters, and you run it again. And you do this repetitively and iteratively several times until you get the performance to 60, 65, 70%, some level at which you think that the model is now performing at a level of acceptance, at some preferred level of acceptance. So you then deploy the model, and now instead of test data, you give it actual, perhaps consumer data or patient data or financial histories, whatever the model is supposed to do. And you now run this deployed model for some length of time, and you collect a lot of information about all the predictions that the model has made, all the kinds of inferences that the model has responded with. And you collect all of that, and you want to now retrain the model, which means that you that you retune the parameters, and you now run the model training algorithm again, and you produce a new model. And hopefully when you test it again, you find that you have now a better learned model. The learnability function of the model has become better. It is a data pipeline, except the data pipeline is now running in a sort of iterative fashion: training, serving, retraining, retuning, training, serving, retuning, deployment, etc., etc., etc.
Exactly.
So
and I think the iterative nature of these sort of models is what make them impressive. A lot of the conversations I have with people that are either trying to utilize something like this or completely against it don't seem to understand the difference between something like this and just simple Boolean logic based on data. And it is that iterative process that makes this something that is such a powerful technology. So I think it's a really good graphic and a really comprehensive explanation as well.
when you run a model today, when you go to ChatGPT or some of your other favorite models, it is worth remembering that weeks and days and weeks and hours of time have been spent in training the model before it was deployed. And the amount of data that it was fed during the training and retuning phase is sort of enormous. Enormous amounts of data have been done. And a lot of that data may have a lot of private components in it, or privacy considerations would apply. And all of that data is being fed into the model. And because we're talking about textual data, reports, medical reports, financial reports, all in different kinds of information, images, etc., a lot of that can't be cleaned up and tokenized. You cannot remove all the private components in this data. So you have this additional burden that you are not only training your model on lots and lots of data, but a large percentage of that training data is going to contain private components.
Right. So that brings up a compliance concern, because if this data isn't tabular and can't be indexed easily, it's possible that you could either miss something during de-identification, or what do you think some other risks are there?
If you cannot de-identify the data because of the nature of the data is complicated, if it's textual data, etc., it is statistically impossible to clean the data up completely. Perhaps you may not want to clean the data because the most powerful models depend on using private data,
right?
Private components of the data. So perhaps you cannot completely anonymize the data. Perhaps you do want to have certain components. You need street addresses or some other such piece of information. How do you do this without violating the regulations that are in force today and the new kinds of regulations that are being contemplated? That is going to be a very, very interesting and difficult proposition of making sure that there is risk avoidance or risk mitigation and compliance. And that is what the Gartner report was talking about, that it's quite possible that some heavy fines will occur in the short-term future.
Absolutely. Yeah, so this brings us to the idea of what some of these specific risks and concerns are in relation to training some of these models. So would you be able to walk us through what some of those look like?
Yes. So now let's look at, as I've said before, the building of models consists of certain phases, and there is a training phase and there is a serving phase. In the training phase, as I said, is mostly quite data intensive. And you are required to process large amounts of data. So the threat vectors at that time are third parties who have access to the data. And if that data has private components in it, and a large percentage of the data sets do have lots of private information, how do you manage, how do you make sure that the accesses, in fact, are authorized? So that is one set of problems. The second set of problems is that the people, if there is a threat from an insider or somebody who has gained root access or has admin access, then how do you prevent these kinds of insider threats? So data-intensive computations, and computations which run for hours and over several days, and there is this huge amount of data being processed in a data pipeline. We need to protect access to the data. We need to protect the confidential and sensitive components of the data that are being fed into the model training process. Once that has happened, at the next phase, you have now deployed the model. And in this case, certainly the inputs that are being fed to the served to the model that has been deployed is almost certainly going to consist of private, confidential, sensitive information. It may be patients whose medical tests are being fed into the model, and certain disease diagnosis, etc., is what the model is being asked to do. You need to protect the consumer, patient, financial data that is being fed to the model. And you need to protect the integrity of the model itself, because if a malicious entity corrupts the model, that model will start to spit out biased inferences, or even making certain subtle and not so subtle mistakes, which may be extremely dangerous and cause all kinds of problems to the user community. So those are some of the risks. And again, it goes back to the idea that during the running of the model in the serving phase, you really want to keep a log of all the processing and all the results that the model has done, because it can be used for retraining purposes.
Mm-hmm.
And if you're going to use the data that you collect in the running of the model for retraining, you need to make sure that the saved collected data itself remains untainted and has not been messed around with. So machine learning is essentially a data-intensive process, and data-intensive processes have the onus of protecting against unauthorized access to the data and protecting the integrity of the results and protecting the integrity of the model. So those are some of the problems AI model security brings to this picture.
So this is where I think things start to get extremely interesting, because I think most people are familiar with traditional ideas of encryption, or rather more common encryption concepts, such as obviously encrypting your data at rest, encrypting your data in transit. But something we can discuss here as a potential remedy to some of these concerns is the idea of confidential computing, which is, of course, the concept of protecting data while it's actually in use. So while it's being used to train these models, and that iteration is going through that cycle, how can confidential computing, address some of these concerns?
Well, we have to be careful. Confidential computing is an interesting technology, but there are limitations that it comes with. As I've said, the model training phase has a lot of manual components in it. It's an inherently repetitive process in which you repeat the training process over and over and over again. In such a case, multiple eyes look at the data, and it may not be possible to hide the data or to, in fact, encrypt the data at all times and sort of hide the data from all the users who are doing the model training process. So I see limited encryption use in parts of the model training process. Certainly, there are phases when you run the model training algorithm, you can certainly use encryption in use technology. But when you are retuning the parameters, you will need to look at the data. So there are parts of the model training process in which certain forms of encryption can be used. When you extract the data from the data lake, you can use encryption in transit or data in transit. When you store it in the data lake, you should be using data at rest or encryption at rest technology. And when you are processing the data, you can use encryption in use, or the idea of secure data enclaves. But when you are retuning the parameters of the model, it may not be possible to use encryption in use. So one has to know. Now, when you are using the model in the deployment stage, a very good use of secure enclave technology is to encrypt the model that has been deployed, and only allow the model to run inside of secure enclaves in the serving state, so you can protect the integrity of the model and protect the data that the model is being used to ask for inferences. I see the use in different stages of secure enclave technology and of encryption technology, but not 100% all the time, but in a lot more in the serving phase of machine learning, when the model is being used in the deployed stage, and some stages of the model training process as well. So I've brought up this idea of secure enclaves. I can sort of explain through some simple pictures what it means. The idea of secure enclaves is that there are now a new class of machines that are being manufactured by the hardware manufacturers. And these machines are now generally available on all the major cloud providers, Azure, Google Cloud, AWS, Amazon, etc. And these machines have cryptographic capabilities built into the chipsets itself. The CPU instruction set uses the hardware's cryptographic capabilities to create these private, isolated computing environments that are sometimes called secure enclaves. So think about the software constructing a region of memory which is free, which is totally isolated and protected from every other process on that machine, or every other VM on that machine, every other virtual machine. So you, in some sense, if you create such a process, such a region, you now have the absolute guarantee from the underlying hardware itself, from the hardware instance itself, that your computation, the data and the algorithm that is being run, or the model that is running or being trained in that region of memory, is completely isolated and protected. And there is no exfiltration of data, there's no leak of data, and nobody else is looking or gaining access to the data.
Right. It's that idea of a hardware root of trust. So the only thing we're really placing implicit trust in is that piece of hardware, is that chipset, right?
Right. This is, you are trusting the hardware, you're taking every other entity out of the trust equation. You are not depending on the cloud service provider. You're not depending on the platform provider. You are now depending on the mathematics of cryptography, which is built into the hardware chipset to say, you are protecting the boundaries of my secure enclave. You are protecting the access based on the mathematical properties of the cryptographic features. You are protecting the boundaries of this secure enclave and protecting the access parameters to my data and to my model. And that's a new paradigm that has been made possible by this new advance in hardware technology. Now, it's not having the underlying hardware is one thing, but having the software to activate these secure enclaves and to run these secure enclaves and have multiple secure enclaves to process the workload as you use and scale up your workload requirements, the amount of computation that you need to do. You need very good software that will manage all these secure enclave technologies for you, so you can concentrate your effort on training and serving the model and not on managing the secure enclave technology itself. It should be done for you by the underlying software or platform software that you are using.
So Shamim, based on the idea of confidential computing and the fact that it does allow the encryption of data in use, how is this a potential solution to some of those concerns we raised related to the training of AI models?
So this notion of confidential computing is more generally referred to as trusted execution environment technology, TEE technology. And this TEE technology has been developed by Intel and AMD and folks at IBM and a lot of other manufacturers. So these are general purpose machines that have cryptographic features built into the chipsets, which can be invoked by specific instructions at the CPU level. So in that sense, these cryptographic features, when invoked, allow the construction of isolated and protected environments in which your computing processes can run. So now you can see that you can take your workload, which consists of a machine learning model and the data, and you can process that machine learning model and data in a trusted execution environment, which is also sometimes called a secure enclave. So once you put the workload in the secure enclave, it is completely isolated and protected from every other process or a VM instance on that machine. And this isolation and protection guarantee is made possible by the underlying hardware itself. So you're not depending on some cloud service provider or some other layer of security. The hardware is basically attesting to its own security level. And the hardware produces a certificate and an audit log that shows you that the isolation and protection guarantee was enforced while your workload was being computed. This, in simple terms, means that at a fundamental level, no other process can get unauthorized access to the computation happening, to the workload being processed inside the secure enclave. So if you have a workload and the workload is encrypted, and you bring the encrypted workload into the secure enclave and you decrypt it using the keys provided by the hardware inside the secure enclave, then no other process can ever see the decrypted data. Therefore, you have this complete isolation and protection at the fundamental machine, at the machine scale level. And this level of protection is now generally available on all the major cloud providers. It's available on AWS, it's available on Google Cloud, it's available on Microsoft Azure. And in fact, there are multiple types of technologies available that fall under this umbrella of trusted execution environments.
Understood.
So let me now do a little plugin for SafelyShare. SafelyShare uses trusted execution environments or secure enclave technology and produces software that allows you to create secure enclaves, allows you to take secure enclaves and connect them to other secure enclaves. In fact, you can have a directed acyclic graph, a network of connected secure enclaves, and you can distribute your workload across this network of secure enclaves and process it. You can have complete isolation, and you can tie the model that is a part of your workload to the data. And so only the model can process the data. The data can only be processed by the model, and no other model and no other data can ever enter into that completely isolated and protected environment. So this is hardware enforced with an audit log.
And that hardware enforcement, Shamim, is where we arrive at this idea of security from the inside out, which is just a fundamentally different approach to cybersecurity. Rather than adding additional layers, you're now just actually changing things, like suggested here, from the inside out.
Yes, you are not following the usual practice of adding layers to protect certain parts of the workload or the computational process. You are fundamentally depending on the cryptographic capability of the hardware itself to provide isolation and protection. So this is privacy by design. Your data is never exfiltrated. Your data is never subjected to an unauthorized access. Only a predetermined model with a known identity, a cryptographic identity of the model can access this data. And no other model with a different identity can, or a program with a different identity can access to the data. And as I said, these capabilities are now generally available on all the major cloud providers, Amazon,
right.
Google, Microsoft Azure. Another big feature of this technology is that the SafelyShare platform provides an audit log of all the events that happen in a secure enclave are now recorded, and this offers an immutable, tamper-proof record log of all the events that happen inside the secure enclave. So you can now do your governance and compliance reports, audit reports, etc., to this technology of audit logs. You can use a SafelyShare platform, as I said, on multiple clouds. In particular, you can do federated learning, in which you can bring multiple data sets and feed them, do either model training or multiple serving models can be used in a federated manner. So multiple data sets can be used in the model training process as well. You can use it for model serving, in which you are guaranteeing the integrity and the uncorruptibility of the model itself, which is doing the serving. And you can have a dynamic clean room capability in which different data sets are being processed by the model, or you can combine the data sets that have been injected into the clean room and do that. You can do all of this across multiple cloud providers using different kinds of TEE technologies.
So it is something that's cloud agnostic and not dependent on one particular secure enclave technology, of course, right?
Yes, there is no cloud lock-in. As I said, the one of the basic ideas, one of the basic value propositions of confidential computing is that you take the cloud service provider out of the trust equation. You are now running a private cloud version. You are using a private cloud for your workload, as opposed to the providing a workload to the cloud service provider who runs it and is a part of the trust equation. So key management is a vital part, because the platform provides the keys inside the secure enclaves. A big problem in platforms that use encryption is the management of the keys. In this particular case, the keys are being managed by the secure enclave technology itself. So you, the platform owner, safely share in this case, or the model owner or the data owner is not burdened with the work of managing the keys used for encryption and decryption purposes. It's all being done by the underlying hardware itself.
Yeah, and that's an important point, is the idea of key management and the fact that it's physically impossible to obtain these keys since they do exist within that secure enclave, right?
Yes, it's physically impossible in the sense that you cannot go and take a hacksaw to the machine. I mean, even
Right.
if you did that, there is nothing that you can do other than physically destroy the machine. There's no way to computationally extract the keys because they are hardwired into the machine itself. So let me, having spent a few minutes talking about it, I think it would be very useful for our listeners to understand a use case that we're talking about. As you know, Gabriel, a lot of models are being built for the medical community and the processing of healthcare data sets. So here is an example of a pharmaceutical company that is interested in running its models on de-identified data. So the first graphic on the top shows a DID extract, and a model is being brought to bear on that DID data, the de-identified data extract, which is being provided to the model. And the model runs and produces an output which is then provided to the viewer. In this particular case, this is the model serving example. The model is protected. It's all running inside a confidential sandbox, which means that in the previous slide, I mentioned the idea of a confidential sandbox or a confidential clean room. So this is an example of a model serving approach in which the model is injected into a clean room which holds DID data, and the output is then provided to a viewer. In the second graphic, the pharmaceutical customer is interested in taking a private data extract, by which I mean data that has some private data components, and join it or union it with a DID extract, combine these two data sets, one containing de-identified data, the other containing private customer data, and provide the combined data set to the model, which is brought into the confidential room to the clean room, and provide an output to the viewer. In this way, you can mix now data that has confidential components and sensitive components with data that is perhaps provided to you in a de-identified manner. And in the third graphic at the bottom is the most interesting case. As you know, a lot of healthcare data is provided in a de-identified fashion. In this example, we are showing non-de-identified data. So the data has not been anonymized, and that is provided for processing purposes to the model. The model produces an output, and then the output is de-identified before it is provided to the viewer. So this is a very different approach, radically different from the normal practice in which the healthcare industry today usually and traditionally de-identifies the data first before it is put to a model. In this particular case, the de-identified data provided to the model is not de-identified, is not anonymized. The model runs on the sensitive data, non-anonymized data, produces an output, and the output is cleaned, processed, de-identified, anonymized, and that cleaned output is then provided to the viewer. So,
and this is an important use case, right? Because as we described before, when you're working with better data, even if that means it's pre-de-identification, the model's going to produce more relevant results as well, even if it's working within a confidential environment. Since we're working with better data to start with, the output might be better as well.
Right. It utilizes the full power of the data because nothing has been subtracted from the data. Nothing has been removed from the data. You provide the full data set in its completely unanonymized fashion to the model. The model processes the data, does some powerful learning, and produces a result. And then you clean the result before you give it out to the viewer. So this is a radically different approach, and we believe that this approach will provide better learnability and better quality results, and yet at the same time maintain the privacy of the data, maintain HIPAA compliance, and satisfy the regulatory bodies. Let me summarize then. The Safely Shared platform is powered by confidential computing. It runs on a number of public clouds, and it turns these public clouds into private clouds where your machine learning workloads can get the security, isolation, and protection afforded by confidential computing technology. You can have asset-level policy-driven access control. So only certain models can access your data. Only pre-specified models can access data, and no other, unless it is authorized. A model, each model has a unique identity, a notion of a unique identity, and only pre-identified models and authorized models can access your data. We believe that this allows you to create a computing environment which protects your data and your models. It allows you to share your data and your models, and it allows very interesting new transactions of data and models. And it's all fundamentally available in a cloud, in a multi-cloud architecture in which the data satisfies, in which the model processing is powerful and satisfies the GDPR, HIPAA, and all other such compliance regulations. Thank you for inviting me to this session. It was very pleasant to chat with you. Thank you for all your questions and your help.
Okay, fantastic. Thank you so much, Shamim. It's always a pleasure chatting through the platform with you. And to the audience, thank you so much for watching live or watching after the fact. If this is something that you think represents a potential use case or is just something you're fundamentally interested in, please feel free to drop me a line at my email at the bottom of the screen. We're happy to schedule a demo and talk through a little bit more about the platform. But thank you, everybody, so much.
Thank you.